Swayam Prabha. Digital India. Educated India.
Okay, so we had an exhaustive discussion on emissivity, the first and foremost of the radiative surface properties, which characterizes the efficiency with which a surface emits as opposed to a black body. Black body is the benchmark. There is no black body, but there are bodies which come close to black body, but any real body will have an emission less than that. So the ratio of the emission divided by the emission of a black body is the emissivity. There is a grammar or nomenclature associated with this: directional spectral, directional total, hemispherical spectral, hemispherical total. We did all that. We did integration, how to convert directional to total, how to convert spectral to directional to hemispherical and spectral to total, and starting from directional spectral to hemispherical total we have seen. Now the next important property is absorptivity, because oftentimes we are interested also in the absorption. It is not only the emission that we are interested in. For example, if your application is solar collector, okay, suppose you want to intercept the solar radiation, you want to have a surface which absorbs lot of radiation in the visible part of the spectrum. Once it absorbs from room temperature of 30 degrees centigrade, if the temperature of the surface goes up to 80 or 90 degrees centigrade, which is about 363 or 373 Kelvin, from the Wien's displacement law, lambda max T is about 3000 micrometer Kelvin. So if T is about 400 Kelvin, this lambda max will be around 9 micrometer. So the body which is heated by the incoming solar radiation, which is at a temperature of 80 to 100 degrees centigrade, will emit in the infrared part of the spectrum. Now if I have a surface which emits very poorly in the infrared part of the spectrum but absorbs very well in the visible part of the spectrum, I have a good solar collector. By the same token, if I have a surface which absorbs very poorly in the visible part of the spectrum but emits very well in the visible in the infrared part of the spectrum, it may be a candidate for an insulation. For example, the sun control film which is put on your on the vehicles, cars, it cuts out the transmissivity is very poor. The amount of solar radiation which comes in is very poor. From inside you can see outside, from outside you cannot see inside. So we have seen ads of Saint Gobain and all that, right? Somebody pours water, and this is very famous. So we will actually see problems how the sun control film works, how efficient it is the information which is given about these surfaces really true or whatever. So first we have to discuss about the story of radiation incident upon a surface. What can happen to that radiation? Okay, so we have to start with that discussion, and it will logically lead to properties. Then again, as usually we will integrate over solid angle, integrate over this thing, and we will have spectral, directional, total, hemispherical, all these properties. Then once we are through, now since the broad framework is already provided, because I told you the broad framework in the context of emissivity, we use a similar framework for absorptivity, reflectivity and so on. We can quickly go through this exercise so that we can concentrate more on practical problems. Okay, now we have to look at apportioning of radiation incident on a surface. Let us consider a surface. Radiation is incident of the surface. I will say incident, that means it is incident radiation watts per meter square. Is the configuration clear? So what all can happen to this incident radiation? What all can happen to this incident radiation? It can absorb, that way, okay? We will track the story later. If it's absorbed, its internal energy will increase, its temperature will increase, then how its temperature is maintained constant, then I will send a coolant and all that. That is not the story now. It can absorb, okay? That is not the only thing it can do. Can reflect. Or if it is a glass or a transparent or a semi-transparent medium, it will allow something to go through. So if you apply the first law of thermodynamics to this system, if you apply the first law of thermodynamics to this surface, don't worry about emission and all this. We are tracking what is happening to the incident. Then from the first law of thermodynamics, mathematically we can state that incident radiation must be equal to from the first law Q incident equal to Q absorb ABS is absorbed, REF is reflected, TRANS is transmitted, okay. So dividing by Q, I can divide by so right side the three terms are all dimensionless ratios, none of which can be greater than the Q incident. The sum of all these can be 1, individually nothing can be more than 1. So they are also some measure, they are also measures of the efficiency with which the surface absorbs, the efficiency with which it reflects, the efficiency with which it transmits, okay. So Q absorbed by Q incident is called the absorptivity, it's called alpha. Q reflected is called the reflectivity rho, this is called the transmissivity tau, okay. So of course we are talking about hemispherical total quantities. I am already the integrations are done with respect to the angle and the wavelength. This is just to introduce you to the concept. We will go through this individual absorptivities and reflectivities as we proceed with this lecture, right. So the important story is alpha plus rho plus tau equal to 1. What is tau for an opaque surface like the human being or the wooden surface or whatever? Transmissivity of an opaque surface is NDT, so you will say something. Huh?
I thought visibly opaque.
No, true.
Yeah, that's it.
Huh? Wow, what is the problem with Jason now?
No, sir, it's
Visibly opaque, it's throughout it's opaque, man, full part of the spectrum. Okay, fine. Okay. So for an opaque surface, But if you pass X-rays, the X-rays come out of us? How much? No. How much?
Bones will not but
Huh?
bones will not.
I don't think so, but we are able to take picture of the bones, everything, right? Yeah, but after that it comes out or? Okay, but that is, we are not talking about, that is of interest to the high energy physicists. That's a very special case. We can't use that case to argue our general argument, correct? Generally you can say wood is opaque, okay? So, but students are not opaque, isn't it? Okay, so for an opaque surface tau equal to therefore so what then remains? What is the logic behind all this? Okay, we did some energy balance, we introduced some quantities, all that is fine. But now I have 4 animals to deal with: emissivity, reflectivity, absorptivity and transmissivity. I killed one of them when I said it is opaque surface. I made him 0, tau. Now I have 3, but now I am trying to see if further simplifications are possible. Now suppose emissivity is known, I am able to write alpha in terms of rho. Now what then remains? Alpha and emissivity, any relationship? Why you are already making the, you are telling the climax man, who said alpha is equal to emissivity? But that is also only for a special case. Any relationship? So the best minds not only worked on finding out the correct black body distribution, when they are looking at the properties of surfaces, they were also preoccupied with the idea of whether the emission and the absorption, or the emissivity and absorptivity, are related to each other. Why? It is for convenience. Suppose I am able to establish a relationship between alpha and emissivity, then if I measure emissivity, then if I know there is a relationship, right now we do not say whether it is equal or not equal, whatever. Suppose from emissivity if I am able to get the alpha, from alpha I can get the rho, and for the opaque surface I know tau is knocked off. Therefore with just the knowledge of emissivity I have all the properties required for carrying out my radiative transfer analysis. Of course other things are there, that is what is the geometric orientation between the surfaces, how to put it, set it up as a system of equations, and solution of equation, that comes later. But fundamentally 2 important hurdles have to be crossed. First is the fundamental radiation laws, which you have already seen, the Planck's distribution for the spectral and Stefan Boltzmann's law for the integrated. We have crossed that. Now we are going through the second most important hurdle, which is the properties. Once you characterize a surface, you also know the black body behavior, then the geometric orientation, how each surface looks at the other surface. If you are able to figure out that, then it is just a system of equations and you solve. Is that okay? Now why do you think there should be a relationship between this and this? Can such a relationship come from theory? That is a black body, but now we are talking about a real surface. Thermal equilibrium is different. Since the physical mechanism of absorption and emission are different, we do not expect any logical relationship between emissivity and absorptivity to flow from theory. So the relationship must come from experiments. Fortunately people have done experiments and then they have founded some relationship. Before we go into all this, first we look at what is called the Kirchoff's law. Okay, have you already studied this? consider an enclosure. You consider an enclosure at a temperature T. So inside you have vacuum. Now you have a body. Now you have a body initially at now for a change I do not have a black body, I have a body whose spectral directional emissivity is given by alpha lambda dash. Okay, I have a real body. So this emissivity is given by what does the second law of thermodynamics tell you? If Tw is different from T infinity and Tw is greater than T infinity, what will happen is, because there is vacuum, there is no conduction and there is no convection, there is only radiation which will take place. Eventually this body will also reach a temperature, this body will also reach a temperature of T. Is it okay? Now what is the story? Okay, there is a body which has emissivity epsilon lambda dash, it is in an enclosure. Now the story is, I put some filters. The filters are basically band pass filters. The filters will allow radiation only in a narrow wavelength interval d lambda to cross the boundary. Okay, and now I can have as many filters as possible in as many wavelength intervals as possible. Suppose I have one filter in a particular wavelength interval, let us say between 3.6 micrometer to 3.7 micrometer only, it allows the radiation from the body at the center to reach the wall. What will happen? The radiation which goes out of the body in the center, which reaches the wall, can only be the radiation which is in this wavelength, because any other wavelength will be reflected by the filter and it will be eventually reabsorbed by the body. And since the body is in equilibrium, it must absorb exactly the same as much as it emits, so that it remains at a temperature of T. But since the body is allowed to emit only the wavelength interval d lambda, which the band pass filter allows, it can also absorb only in the same wavelength interval d lambda, and this d lambda is under my control. I can change d lambda from 3.5 to 3.6 or 8.9 to 8.1, 8.9 to 8.6 or 8.8 to 8.9, whatever I want. Therefore, under these conditions, since the body is both emitting and absorbing only in a particular wavelength interval, I can also choose the direction, right? I can also make the filter in such a way that it will permit in only one direction. But we are taking recourse to the second law of thermodynamics, which forbids the body from being at a temperature which is different from that of the surroundings, because eventually equilibrium will be established. Therefore what happens? Epsilon lambda dash, okay, let us say, okay, therefore dq absorbed must be equal to dq emitted. Is that clear? dq absorbed equal to dq emitted. Now there is a small problem in the sequence of the story. Right side you can evaluate epsilon lambda dash I b lambda cos theta d theta sin theta d theta d phi d lambda, all that you can. But dq absorbed, in order to do dq absorbed, we now need to define spectral directional spectral directional absorptivity. Okay, so we have to hold on to this. So Let us revisit this after we have defined this. So, how do you define spectral directional absorptivity? Can you tell me? From dq absorbed. Alpha lambda dash, lambda, the temperature of the absorbing surface, theta I, phi I will be equal to dq absorbed divided by not black body, divided by how much is absorbed divided by how much is incident. Incident is I lambda I multiplied by all those things. Can you tell me? I lambda I, lambda T multiplied by cos theta I, sin theta I, d theta I, d phi, d lambda. What are the units of the numerator and the denominator? Denominator, what are the units? Watts per meter square per micrometer, watts per meter square per micrometer per steradian. Sin theta, d theta, d phi is what? Steradian. D lambda is what? If you want, let us consider two unit vectors. Okay, so this is theta I. Yeah, please look at the board. Okay, so if some people have a doubt whether dA will come, this can be made as dq absorbed, or shall we put dA here? I can declare that this is watts, right? See, this is all what we create for us to understand. Finally, we should not die because some units are not, we can adjust all this, okay? Are you getting the point? Now, something is absorbed divided by something is incident. That incident I am relating to I lambda I, okay? So, this I lambda T may also be, if you want you can also put it as I lambda T theta I phi I, because it may not be incident from a black body. Let us not see this definition itself, we can spend half an hour, 1 hour on what are the things for, I mean what are the terms which should be contained within this brackets, correct? I lambda T, why should the incident radiation not be a function of theta I phi I? When will that happen? If it is incident from a diffuse body, okay? So already make an assumption. So if you do not like it, have this also, I have no objection, but as students of engineering radiation, I want you to know that you should multiply I lambda by cos theta sin theta d theta d phi d lambda dA and set it as a denominator. A numerator, if you know dq absorbed, if you have a meter or an instrument which measures this, you can get the spectral directional absorptivity. Now, using these arguments for the enclosure which we use for deriving the Kirchoff's law, so you know that alpha lambda dash let us ditch the dA into I lambda correct, I lambda theta cos theta I will put d omega I, d lambda is equal to this T and this TA, what is the problem now? When you apply it to, be very careful about for this. The surroundings of the enclosure and the body all are at, what is the temperature? T. So I should not use T, right? Okay. T. If you don't like d omega I, you are welcome to put sin theta I, d theta I, d phi, I have no problem, right? Yeah. Now, what is the equation number for this? I will keep this as 1, I will keep this as 2, keep this as 3. It is true regardless of, the direction and the, yeah, any problem? No, I am writing the expression for dq absorbed and dq emitted. dq absorbed I am writing in terms of the emissivity, absorptivity, and dq emitted I am writing in terms of the emissivity. Okay. So to cut a long story short, the spectral directional absorptivity is equal to the spectral directional emissivity. This is the Kirchoff's law. It is with general, it is valid for any wavelength, it is valid for any angle, and don't think it is valid only for enclosure and the body has to be in equilibrium with the surroundings and all that. That is basically to prove. Okay, it can be experimentally verified. This is sort of a proof from argument point of view. Don't think that it is a very shady proof and all that, and what will happen if the equilibrium is not there, whatever. I use these arguments to prove this. So this is called the Kirchoff's law. Kirchoff is again a German. Okay. Kirsche means, anybody went to Germany here? Intern. What is Kirsche? Kirsche means church. Kirsche means church. So it's off the church, I don't know whether it's too off from the church or okay. Kirsche means church. Okay, so always true. And now we can call it 4. Fine. For a grey surface, what is the story for a grey surface? Epsilon lambda dash and alpha lambda dash are not functions of lambda, right? Therefore, for a diffuse surface, there should be I lambda, sorry. That is what Deepak was trying to tell me, or there should be I lambda, sure. Okay. Now, for a diffuse surface, see, the theta I phi I is very important because normally you can keep it as theta and phi or theta and phi. but when you are considering a reflection, here you are considering only absorption. When you are considering reflection, there is a theta I phi I and a theta r phi r, correct? It can receive the radiation from incident can be on one direction and the reflection can be in all directions, it can be diffuse, or it can be specular, that means it is entering in one direction, it is going in one direction only. That is why absorptivity we use I with respect to theta I phi I, but reflectivity will have theta r phi r, it will complicate. Reflectivity is one of the most complicated things. And it is the most fundamental property. Okay, so I will tell you what are the complications associated with reflectivity in tomorrow's class or next week's class. Now, for the diffuse surface, the epsilon lambda dash is not a function of theta phi, therefore is that correct? The dash goes off, right? It is the same in all the directions for gray diffuse surface. For a gray diffuse surface, okay. So for a gray diffuse surface, very important result. For a gray diffuse surface, the emissivity is equal to the absorptivity. This is also equal to the hemispherical total emissivity and the hemispherical total absorptivity, because it really does not matter. Okay. The other important thing is equation 7 is not the Kirchoff's law. It is a post processed version of Kirchoff's law for a gray diffuse surface. Kirchoff's law is more general, it is the spectral directional emissivity equal to the spectral directional absorptivity. Many people will say that Kirchoff's law is epsilon equal to alpha, it is a very special case of that. Now, for a gray diffuse opaque surface, finally what is the overall picture, what is the grand picture now? This is a very common engineering assumption. Suppose I want to find out the radiative heat transfer between the walls of this classroom. The walls of the classroom are opaque, fine, sure they are opaque. Then if I make the assumption that these walls are made up of gray diffuse surfaces, then the walls of the enclosure of this classroom can be treated as a gray opaque diffuse enclosure, which considerably simplifies the analysis. Why? Tau equal to 0. So from handbooks or data books or from experiments, or somebody tells you what the emissivity of the surfaces are, you can calculate the absorptivity, you can calculate the reflectivity, you can proceed with the detailed radiative heat transfer calculations. Okay. Now, before we proceed to the spectral total emissivity, spectral hemispherical absorptivity, I will just give you a sneak peek into what all this will eventually lead to. Because we should be able to relate to the final goal. The final goal of all this is that you should be in a position to calculate the net radiation heat transfer from any surface. This surface may be a surface which is isolated, or this may be a part of several surfaces in an enclosure or in a furnace or combustion chamber, whatever. Now, what is the net radiation heat transfer at a surface? The net radiation heat transfer at a surface is incident, reflected, absorbed. I am talking about at an opaque surface. Now there is also an emission consequent upon the surface of the temperature being at a temperature greater than 0 Kelvin. So the net radiation heat transfer at the surface is what is going out minus what is coming in. What is going out has got two components, the reflected component and the emission component. What is coming in is the incident. Therefore the net radiation heat transfer is reflection plus emission minus incident. If everything is written consistently in watts per meter square, all the three are in watts per meter square, you will get this. So the eventual goal is some fellow may emit, it may also receive radiation from the sun, he may also become hot, and so in between some other things will also take place. Maybe Q is equal to HA delta T, some convective cooling is also there, some wind is also blowing. So if all these things are taken into account, now you look at the energy equation and then you will write all this. If convection and conduction are ruled out, then the net radiation heat transfer at the surface is given by Q net or Q equal to Q is it taken care, no? What is going out minus what is coming in? Huh?
Q net is equal to what is absorbed.
Oh. That is a net radiation heat transfer at the surface. This much has to be removed, otherwise the temperature of the surface will increase. If you do not want to, so what will happen is, if you for a solar collector you have an energy balance like this, then you send your cold fluid and heat it up, and that is how you get the solar water heater. Okay, so you may have, why? That I do not know, Q net is positive or this, that depends on the situation. Okay, if the incident is too much and emitted is less, that is what you want, right? Then Q net will be minus. If Q net is minus or plus depending on your sign convention, accordingly the body will get heated or will get cooled. Okay, now because we have already done the Kirchoff's law, suppose I give you a surface which is like this, epsilon lambda. Is this clear to you? It's a very small problem. What is the question now? Number? 10. Problem number 10. The hemispherical spectral emissivity of a surface is the hemispherical spectral emissivity of a surface. The hemispherical spectral emissivity of the surface is given on the blackboard. Draw the corresponding distributions. Draw the corresponding distributions for hemispherical spectral absorptivity and hemispherical spectral reflectivity. Draw the corresponding distributions for hemispherical spectral absorptivity and hemispherical spectral diffusivity. No math, okay, because I have not defined all these values for you, all these quantities. Okay, alpha lambda and rho lambda, that is what I want. I want the distribution for, can you tell me? Take 2 minutes. Yeah, now you have to go back to the definition of, you have to go to the Kirchoff's law. I have removed the diffuse and all that because I told you it is hemispherical already. Huh? Are you able to follow the question? So, what is the distribution for alpha lambda? Huh? Very good, same as this, okay. What about for reflectivity? Very good, very good. 1 minus this, that is all, you understood this. Now I do not even have to define alpha lambda all that for you, but for the sake of completeness we will do this. So if I give you emissivity distribution, you are able to manipulate and get all the other distributions. However, calculating alpha from alpha lambda is not so straightforward. I need to know the variation of I lambda with respect to lambda, or I should tell you that this I lambda is coming from sun. Are you getting the point? That means I am interested in calculating the solar absorptivity. If I tell you what is the source temperature from where the radiation is incident, then you can consider the sun to be a black body at 5800 Kelvin, treat it as a black body, use F function chart and calculate as if you are calculating emissivity. Otherwise, it is my responsibility, or it is my responsibility to give you I lambda as a function of lambda. Is that clear? Okay. Now let us draw the distribution for, yeah. No. If I know the source temperature, I do not need additional information. If I know the source is from a black body, I do not have to tell how I lambda varies with lambda because I know black body variation. If you do not give me information about whether that is a black body or grey body or whatever, then you give me I lambda as a function of lambda, you draw the graph and give me, then we can calculate. Are you getting the point? Okay. Now so it starts with .8 up to 2, then 0.2 up to 3, then 6.6. So if you have to calculate rho from rho lambda and also alpha from alpha lambda, I need to know the I lambda I. Are you getting the point? Or it is very easy, I calculate alpha first and then use alpha equal to 1 minus rho. That is also possible. Are you getting the point? So there are various options available for us. Okay. Now spectral hemispherical absorptivity. What is the definition? Yeah, alpha lambda is there. What is the TA? I keep writing this TA. What is the TA? Temperature of the absorbing surface. So what will be the mathematical definition for this? I lambda I let us not worry about the temperature. If I tell you the lambda theta phi, that is enough, into sin theta I d phi d theta I, that is it, right? Divided by, yeah. Okay. So if I give you the if I give you the distribution or the functional relationship between alpha lambda dash as a function of this theta, and I also give you information on I lambda I, it is possible for me to multiply alpha lambda dash by I lambda I and integrate it over the complete hemisphere and get the numerator, integrate just the I lambda I over the hemisphere and get the denominator, and this the ratio of these two will give you give me the alpha lambda. Now already there is overdose, so tomorrow's class we will do the directional total absorptivity and hemispherical total absorptivity and start solving problems. Fortunately I do not give you problems where all these are given, you have to integrate and all this. Maybe we do problems like this where the directional effects are already taken into account. I say already it is hemispherical, and okay, but the basic idea behind giving you fundamental definitions is, if you encounter a directional nature of the distribution, it should be possible for you to handle, correct? Okay.